So we are dealing with neutron stars, just some simple things, right? And there are many different observational manifestations, right? Even in isolation, we have radio pulsars powered by rotational energy, magnetar powered by magnetic field dissipation, and maybe fast radio bursts. In binary systems, we have magnetic field, right? Accretion onto magnetic neutron stars, the plasma interactions of plasma coming in with the neutron star magnetic field. Merging neutron stars also interacting magnetospheres. Many people here, a number of people here worked on all these subjects. Okay. Of course, radio pulsars are most common manifestation of neutron stars. You measure the rotation period in P and P dot, you infer the B field, right? Most pulsars have B field of 10 to 12 Gauss or 10 to 13 Gauss. The subset of radio pulsars have lower field, 10 to 8, 10 to 9 Gauss. And then, of course, in the last 10 years, there's also a small number of radio pulsars have B field approaching 10 to 14 Gauss. We call it high field radio pulsar. And of course, radio pulsar emit radiation in all wavelength band, thanks to all the complicated processes in the magnetosphere and near the surface. Okay? And then, of course, still many odd behaviors that we don't understand about radio pulsars. The favorite thing I like to say about this so-called intermittent pulsars, where you see the pulsar happily active for a few weeks and then quiet for another few weeks and then become active again, and this bistable states is very intriguing. And of course, we think all these are due to the fact that we have this unipolar inductor, like the combination of strong magnetic field and rotation giving rise to a large potential drop across neutron star surface, and that transmitted into the magnetosphere, giving rise to all kinds of cascade particle acceleration process and giving rise to radiations, right? We have experts here working on this. You can ask them, right? And of course, magnetars, and these are neutron star powered by super strong magnetic fields, right, with field greater than 14 Gauss. And why do we say that? Because even in quiescence, when the neutron star is boring, it's just quiescent, and you observed the magnetar in X-ray band, from soft X-ray to hard X-ray, you find the luminosity is very high, higher than the rotational energy loss rate. So I omega dot is the rate at which the rotational energy is being depleted, right? You measure omega dot in X-ray for many magnetars. So even in quiescence, the luminosity is higher than the spin-down luminosity. That means the energy must be coming from something else. The most plausible thing is that it's coming from magnetic field dissipation, right? So the typical magnetar has surface temperature of few million kelvins, few million kelvins, but also there's energy going all the way up to 100 keV, indicating there are very active corona magnetosphere surrounding the magnetar. Right? And magnetar, of course, have all kinds of bursts, flares, right, including giant flares, where you emit a lot of energy in a very short period of time. And all these, we think they are maybe due to some kind of starquake agitating the magnetic field, giving rise to dissipations, right? And unlike radio pulsars, magnetars do not show persistent radio emission, but they do have transient X-ray emission, perhaps triggered by some starquake and X-ray emissions, right? And then finally, at least one FRB, we think there are magnetars, the galactic magnetar that was observed to show FRB fast radio burst-like behavior, and preceded by X-rays, so X-ray bursts. So at least some FRB are produced magnetars. And people don't work on neutron stars often ask the question where the field come from. There are two possibilities, two ideas. One, of course, the field was already there in the core of a massive star, the progenitor of a neutron star, and then the star collapsed. The field gets amplified by flux freezing. Another idea, of course, being known for a long time, is that the newly formed neutron star is violent, it's convective. It's highly unstable and has all kinds of fluid motion giving rise to dynamo processes generating strong field. Okay, now of course, going back to the theme of this session, there are all kinds of exotic QED processes that's happening when you have a strong magnetic field. For example, one photon pair production. You often give this to the undergraduate student, right? If you have pure vacuum, photon cannot automatically convert into pairs, because you cannot conserve momentum energy simultaneously. But when you have strong B field, the magnetic field can absorb momentum, and this becomes possible, right? And this becomes very efficient. one photon pair production. Similarly, photon splitting can happen. This is forbidden, in normal physics, but with QED, this can happen, right? And finally, there is another example which I'm going to talk about in the next 20 minutes. It's so vacuum polarization effect. The fact that even in vacuum, when you have a strong B field, the propagation of photon is modified, right? So the vacuum behaves like a crystal, right? A photon propagating that in the vacuum is like propagating a crystal, and right, separated into different modes, right? This may sound a bit strange because photon is a neutral particle, should not experience the B field, right? But of course, until you remember that photon can be temporarily converted into pairs, the pairs are charged particle, they experience B field, right? And therefore, the photon propagation will be affected by the B field, external B field, right? All this QED process become important when the B field becomes very strong. The critical QED field strength is set by equating the electron cyclotron energy. If you know the electron in the strong B field is the transverse motion is quantized into Landau level, right? This typical spacing of the Landau level is h bar times the electron cyclotron energy, right? If you equate that electron cyclotron energy to the rest mass energy of the electrons, you get QED of 4 times 10 to the 13 Gauss, and this is critical QED field strength that I'm sure you're going to hear a lot about. Okay, now this now going back to this vacuum polarization effect, right? These have been known, well studied for a long time, right? According to QED, you can calculate these kind of things. Now you don't have to know anything about QED. All you have to know is that because of QED, the dielectric tensor of the vacuum is not unity. It's I is not unity, but there's a correction delta epsilon. Vacuum is a tensor there, right? And that tensor has all kind of complicated things. But in order of magnitude, the element of that tensor is of order 10 to the minus 4 in that formula, right? So now 10 to the minus 4, where it comes from is alpha divided pi square, all that kind of QED thing, if you remember. That's why. So even at B equal to BQED, that correction is of order 10 to the minus 4. So even at 10 to the 15, this is only like a few percent, right? Okay. Now, because of this correction, the vacuum become crystal, right? It's very stringent. So you have two distinct photon polarization modes that have different phase or group speed, phase speed, right? The index of refraction. Okay. And you get two modes, right? One is we call the ordinary mode, where the electric field of the wave lies in the plane of K and B, K being the directional propagation, B being the external field. So this ordinary mode, they're the component. The E field of the wave is in that plane. And the extraordinary mode has the electric field perpendicular to that plane. The plane stands by K and the external B. Okay? Now, as I said, these two modes have different index of refraction, different propagation speed, but the difference is very small. Even at 10 to the 15 Gauss, the difference is only a few percent, 5% or so. It's a very small effect. You may say, well, why bother? Because there's so many other complicated plasma things going to happen. Why do you bother with such a small few percent effect? So you're going to hear that in a few minutes. So I'm going to explain. But before I do that, let me first go to the new observation. In a few years ago, NASA and the Italian Space Agency launched this IXPE, right? It's a soft X-ray polarimetry mission. It can measure the X-ray polarization of bright sources in low energy soft X-ray band from 2 to 8 keV, measuring X-ray polarization. So this is actually opening up a new window in X-ray astronomy. Okay, right? And so they in 2022 they published their first science result describing detecting the polarized X-ray from a magnetar. This particular magnetar, right? It's a known magnetar known for already before, right? It's at the period of 8.7 seconds, a very ordinary magnetar, right? From a P and P dot measure the X-ray. People already know this, right? From PP dot, you infer the dipole field using a simple dipole formula, right? You infer the B field is 10 to 14 Gauss, okay? And this is known. Also, people looked at this before. It's In the soft X-ray band, the X-ray can be described by a black body radiation, 5 million Kelvin, plus a little thermal component, and maybe another slightly hotter X-ray black body. Okay. Now, what's this XPE found? XPE found is that they measure the X-ray polarization in low energy band. Of course, they don't have very good energy resolution, so they divide the energy band into two bands. Low energy, 2 to 4, and high energy, 5 to 8, right? In low energy, it's linearly polarized, 14%. In high energy, it's also polarized, 40%. The only thing that's interesting is that this it's both polarized, but it's perpendicular. These two, at low energy is this way, and high energy is this way, okay? Perpendicular, there are 90-degree swing across energy, okay? So that's what it is. That's what this is. You see here. Okay, you see this here, right? Low energy this way and high energy this other way. Okay, and the paper, they suggested that this may be explained by a condensed emission from condensed or part of the condensed neutron star surface plus some Compton scattering in the magnetosphere. Now, the condensed neutron star surface is an interesting thing, right? Meaning that if you have very strong magnetic field, the surface of neutron star may actually be in a solid form. Condensed matter form, right? And that's interesting. I'm actually interested in this kind of things, but this may not work for this particular source. So what I'm going to explain in the next 10 minutes is to consider the alternative possibility that this might be explained, or might be the possibility that this may be a manifestation of QED vacuum resonance that may be naturally account for this kind of behavior, okay, at least. But there are, of course, important caveats we'll come back to toward the end, okay? All right. So now, okay, so this soft X-ray emission, we think they are certainly almost certainly they're coming from the neutron star, the hot neutron star surface. Now, neutron star, we usually think they are very dense, of course, nuclear density, but of course, near the surface, density is low. That's where the photon, the X-ray photon we see, it actually emerges from the so-called photosphere. It's like from the atmosphere, right? Right. We're not talking about this condensed neutron star surface. It's a really gradual thing, right? So this atmosphere consists of magnetized, partially ionized plasma. Cold plasma, basically, okay? The scale height, kT over the mass of the proton divided by g, is very thin, centimeter, simply because the gravity is very strong, right? So within a centimeter also, the density drops very rapidly, okay? So that's the scale height. And the typical density of the photosphere where the X-ray photon come out, emerges, is about 1 gram per cc. It's very convenient. It's like water. Okay, so that's the typical condition we're dealing with, right? Now, when you are studying radiation from this magnetized plasma, the atmosphere, the first thing you have to do is to look at polarization modes, right? What kind of polarization mode you have in this partially ionized plasma. Now, this is, of course, it's a exercise, simple exercise you do undergraduate E&M or plasma physics, right? You basically, the magnetized plasma has a dielectric tensor, which is deviated from the unit tensor, the plasma correction, because wave propagating in that plasma get, the electron will move and give rise to dielectric tensor, right? And this you can calculate. This is a standard thing, right? And then the only thing that's different from the textbook is that you are in the regime where the photon energy, we're dealing with X-ray, soft X-ray, much less than the electron cyclotron energy, which in this case for 10 to the 14 Gauss is about MeV. So we're certainly in the regime where the photon frequency is much less than the electron cyclotron frequency. Okay? Now in this regime, you have two photon polarization modes. Both are almost linearly polarized. Of course, rigorously they're elliptically polarized, but almost linear, right? Again, we have two modes. O mode, where the E field of the photon is in this plane of K direction of propagation, B of the external B field. The X mode has a perpendicular component. Now, why do you care? Why do you care about these two modes? The reason you care about is that because these two modes have very different opacity. They interact with the photon, with the plasma very differently, right? The X mode photon, you can see the X mode photon is polarized in this plane, in this direction, so it has an electric field component along the direction project in the external B field direction. So therefore, the electron sitting there can respond more or less easily, more or less freely with them, because electron can move freely along the field. So the opacity is more or less the same within order of magnitude, same as the B equals 0 opacity. In contrast, the X mode of photon, where the electric field of the photon is perpendicular to this plane, namely it's perpendicular to the external B field. The electron is sort of tied to the B field, cannot move that much. So therefore, the opacity is actually reduced by a huge factor, which is given by omega divided omega cyclotron. And it makes sense, right? Because the electron is tied by the B field, so it cannot move, respond too much, so the opacity is much lower. Okay, so you really have these two modes, each have very different opacities, right? So the result then is that you have two distinct photospheres, whereas X mode photon has low opacity. That means they decouple from the matter deeper. This is a little cartoon amplified. Right? Remember the whole thing is centimeter also, right? So the X mode here, right? So inside the neutron star is deeper, right? It's diffusing. That's we go here, and then at here, the actually photosphere they freely streaming out. The O mode is diffusing, right? And then here the photosphere, right? Two distinct photosphere, right? Now, so the X mode photon come from deeper, emerges from deeper in the star, in the atmosphere. So it's hotter there. So therefore, it has more flux. Right? X mode carry more flux, and therefore, if you put a polarimeter on the neutron star surface, you're going to see mostly X mode. Right? That's why it's highly polarized. Right? So that is okay. Now that's the only part of the story, because I already told you a few minutes ago that in strong field, even without plasma, you have this QED corrections that also make the medium birefringent. So naturally, you have to put them together. Right? When you're dealing with photon propagation in this atmosphere, you have to have two contributions: the plasma contribution, the vacuum polarization QED contribution. Both of these are small, right? The QED contribution I told you is only a few %, even at 10 to 15 Gauss. The plasma contribution, is basically depend on plasma frequency divided by photon frequency square, which depends on density and energy square. So it's also small. Both are small, a few %, right? But however, there's two things, they compete against each other. It turns out they are the resonance, right? If you equate these two things, you find they're the resonance, where it's actually very easy to remember. For 1 keV photon propagating in 10 to 14 Gauss magnetic field, the vacuum resonance is about 1 gram per cc, which happen to be in the ballpark of the photosphere, right? This YE here is the electron fraction, but depending on the composition of the neutron star, neutron of the atmosphere. Okay, now of course, tensors, these two tensors do not cancel, of course. What I really mean is that you just calculate this, do the simple E&M problem, calculate the polarization mode in this dielectric tensor, right? And what you get is this kind of thing. So here it's basically two lines representing two eigenmode of the photon polarizations as a function of density in units of vacuum resonance density. This K here, remember the polarization ellipse, this K here measures the ratio of the polarization ellipse, right? So you see that the two lines, two modes, so at high density, higher than the vacuum resonance density, you get two distinct modes, right? One mode has K the value of K absolute value of K much greater than 1, another one much less than 1. So that means one is this way, another is this way, they're perpendicular. Okay? At low density, you also have two distinct modes, because the low density is dominated by the vacuum polarization. You also get to one mode is, this K much less than 1, another much greater than 1. But but in between, at this thing, you see they try to do this thing. They cross. That's what I mean by compensation. Competing against each other. They don't really, right? This is what you have, right? And at this place, the two modes actually become very similar to each other, except the different helicity. Okay? Now, some people who worked on neutrino physics recognize they're very similar to this MSW neutrino oscillation that's happening in the sun, right? They're neutrino, there are two eigenstates. They have, center of the sun is very distinct, in the vacuum also very distinct. In between, they are the resonance, right? MSW resonance. Similar kind of things will give rise to photon neutrino conversion. And similarly here, you can see, right, if you have a photon created by the matter, which is say X mode, right, or X mode here, and then this photon propagating. If you ride with that photon, you are going to see a gradually decreasing density, right? And then, of course, if you see a gradually decreasing density, you're going to, if you follow along these eigenmodes, and then you're going to basically automatically gradually convert it into this X mode. So what happens is that this photon coming from here, propagating, and then just do this. Okay, the adiabatic conversion. Okay, this does not always happen. There's a condition you have to satisfy. You can calculate that condition. So this condition translates into basically the index of refraction of the two modes should be sufficiently larger compared to the gradient of the density. Or in other words, the density gradient should be sufficiently gentle, sufficiently smooth. So you can convert that thing into this condition. Basically, in order to have this adiabatic conversion to happen, right? The energy for given scale height, right, centimeter or so, density gradient, the photon energy should be greater than 2.5, a bunch of factors, right? keV also, depending on the scale height along the light ray, along the photon ray. Okay, so the point then is that if you have a photon with energy greater than this adiabatic, this E ad, right, you can experience this photon adiabatic conversion. Whereas if you are less than that, there's no conversion. You just probably encounter the resonance. The resonance doesn't matter. You just go. Okay. In general, there's the jump probability. There's strong dependence on the energy. Okay. Okay. So let me recap what we talked about. There are three densities are important, right? I told you there are two photospheres, X mode and O mode photospheres. Right? That's where the two polarization photon mode decouple from the matter, from the atmosphere, from the matter, right? And X mode has low opacity, so it's also, the photosphere is very deep. It's actually very deep in the atmosphere, right? O mode you can estimate this given the opacity. You can estimate the O mode photosphere, is given some formula. And then there are the vacuum resonance density. Okay? So obviously it's important to compare these two. X mode density is very high, so you just need to compare O mode density and the O mode decoupling density and the vacuum resonance density. And it turns out if you do this thing easily, you find that when B is less than some critical value, which is about 8 times 10 to the 13 Gauss, there's a bunch of factors depending on photon energy, depending on the direction, depending on the scale height, all the kind of things, right? Molecular weight. You have for low energy, low B field, if the surface B field is low, right? Then you have a situation where the vacuum resonance is low density, lower than the same, than the O mode decoupling photosphere. Okay, so you have this situation, a low B field. X mode is very deep, and then O mode is deeper, and then it's most shallow region, right? So in this regime, if you look at the problem, let's look at high energy, right? This is adiabatic regime, right? Imagine deep in the atmosphere, you have an X-ray mode photon, right? Diffusing and then freely streaming out, and then encounter this resonance. Then it basically changes polarization, changes the orientation, right? The X mode coming out, diffusing and coming out, and then convert into the other direction. Okay? Right? But this X mode is coming, this line is coming from deeper, so this is thicker. So you can see this, in this case, this is a thicker line. Whereas the O mode photon is decoupled here, and then it get converted to X mode. So you can see in this case, the radiation in the high energy band is dominated by the O mode. Similarly, if you do the low energy, then of course you can do the same thing, but then of course at the vacuum resonance, you don't care. It's not adiabatic. So in this case, you can see at low energy is dominated by the X mode. So you can see in this case, when the surface B field is lower than this critical value, about 10 to the 14 Gauss, the emergent radiation from the atmosphere is going to be, have the direction of linear polarization change direction, right? At low energy is one direction, at high energy is a different direction, perpendicular. Okay, so that might be the reason. Thank you. Yeah, that might be the reason that this seems to be a very nice explanation for this observed low energy. You have this one direction, high energy, other direction. Seems very nice. Okay, and of course, again, this transition is in this particular model theory depends on this adiabatic energy, which is 2.5 times a bunch of things. Now, in astrophysics, 2 often equals 5, right? Of course, but in this case, actually, you actually can care, right? If you want to make this thing E adiabatic equal to the 4 or 5, which is observed, you actually prefer heavy element partially ionized atmosphere. You can actually change the scale height. You can actually do this thing. Okay. Okay, so just recap, this particular source, this 90-degree X-ray polarization change at 4 keV may be associated with vacuum resonance, right, where the low energy and high energy photon are dominated by different modes. Right? If you believe this interpretation, there are several interesting implications. Now, because you know the absolute orientation of the polarization, you can actually infer from the observed X-ray polarization, infer the spin direction by phase averaging spin direction of the photon of the neutron star in the plane of the sky, right? It turns out to be aligned with the direction. This particular magnetar has a proper motion. They actually align, so that's actually very nice. I said this also to explain this. You also need, in order for this to work, you really need a heavy element atmosphere, and you also need. Remember what I said. This B field is the actual B field, the surface B field. You actually need the B field to be comparable, to be actually small, not to be small, less than 10 to the 14 Gauss. Right? The dipole field for this particular magnetar is 10 to the 14 Gauss. Right? So this says, if you believe the story, you actually have the surface field not much larger. It should be actually smaller than 14. So that's actually interesting. Maybe a problem, but it's actually interesting, right? And this actually may be related to this, if you think about maybe this the last few years, this extremely slowly rotating pulsar that have been observed, and this, if you believe this, it means that some of these neutrons are maybe spin down more efficiently than we expected. Okay, so what about other magnetars? Right, there's just one magnetar had this nice 90-degree change. What about other magnetars? So last year they published another magnetar. In this case, it's another well-known magnetars. Has from PP dot, the B field is 5 times 14 Gauss. And then this magnetar has all the, in different energy bands, they're all aligned. It's all linear polarized, no 90-degree. Okay? It just happens the B field is higher. Okay? So in this, it turns out in this regime, according to my story, when B field is larger than this, then you have this situation where the vacuum resonance is actually deeper than the O-mode polarization. You have this hierarchy. In this regime, you find if you do this exercise, you find even though there's a vacuum mode conversion, just an adiabatic thing, because it happened deeper, it doesn't matter. You find that you find that the plane of linear polarization at different energy coincide. You don't expect to have 90 degrees, this switching between low energy, high energy. Although the vacuum resonance can strongly modify the emergent spectrum. Okay, so this perhaps is consistent with this particular source, right? And okay, so let me summarize so far, right? So I told you about this physics of photon traveling in homogeneous neutron star atmosphere can experience vacuum resonance, right? Vacuum for resonance, you have this adiabatic conversion. Okay, thank you. Yeah, and so this low when the B field is low, you have this 90 degree change. High B field, you don't have this thing. This all seems very nice, right? Very beautiful. Except, of course, just last minute, there are the important caveats. I'm hiding this big elephant here. It's been known for almost 2 decades that magnetar it's not just surface black body radiation, has a big important emission at high energy, 20 all the way to 100 keV. So that, of course, indicating that the neutron star, this magnetar, has an active magnetosphere, corona, right? A lot of things happening there, right? And what is the plasma density in this corona? Well, we don't really know, but a nice, appealing picture is that you have a strongly twisted and dissipating magnetosphere, in even close field line dissipating, all right? And if you use Ampere's law, you can estimate that the electron plasma density, right, that depends on twist of the magnetic field. And this twist, because of the twist, the electron density can be very high. higher, certainly higher than gold-right Julian density that normal for low delirium pulsar, right? And this strong plasma, high plasma, mild relativistic plasma can induce resonant Compton scattering of photons from these neutron star surface, right? And this has been, the resonance scattering happens when the photon energy, right? Photon coming from the surface, they encounter resonance at some location where the photon energy match the cyclotron, or photon frequency match the cyclotron frequency. They encounter strong resonance scattering. And many people have studied this thing, so basically photon propagating, they encounter resonance before coming to the observer. Okay? And these can modify the spectrum. So here is just one thing. For example, if you don't, it's a toy model calculation, if you don't have scattering, you get this black line, so you can see 100% at low energy below 4 keV, 100% also above 4 keV, there's a transition. Changing sign means 90 degrees. If you include the scattering, you can, of course, if you depend on the density, you get sort of this amplitude get reduced, but the sign switching is still there. So I would say the scattering can reduce the polarization degree, but preserve the 90 degrees sort of pattern. Okay. Now, of course, this scattering only one part of the story. Then you can do scattering. You really have an active atmosphere can actually do the emission by itself. You may have pair plasma undergoing annihilation process inducing emissions, and that can give rise to the Chris is sitting there. This paper I'm still digesting. That may be, so the worry is that may be the thing. So maybe the contributing there. How much radiation from this magnetosphere is contributing to 8 keV emission? So that's an important question, right? So take-home message, right? Photon propagating in the magnetized plasma, this small QED effect, a few percent, small plasma effect combined together can give rise to, in principle, striking observable signatures, right? And may have been observed, but maybe not. Nature is more complicated. There are all these caveats that I hope we can discuss. And in the future, in a few years, 5 years, there will be a future mission dedicated to X-ray polarization and X-ray timing that will perhaps improve the situation. Thank you. I'll stop. Thank you.
Okay, thank you, John. This is a very interesting talk. Vacuum birefringence is one of my favorite QED processes. It's nice to see there might be some signatures of it astrophysically. So we have plenty of time for questions and comments. If you are near a mic, it would be helpful if you went over there, or you can wait for me to arrive. So I'm going to come to Chris first, and then Yuri over here. So.
Yes.
So pairs generated in the magnetosphere, especially if they're mildly relativistic, will warm the outer atmosphere.
Yes.
How would that change your story?
Warm atmosphere. You are saying that maybe even induce temperature inversion. That's the thing. That's not accounted for. Maybe the thing in that case, yes, the reason that what Chris is referring to, it's normally, I said earlier at the very beginning. Let me just okay, at the very beginning, right? Very beginning here. Right. So two photosphere, right? And that's certainly true, right? And the X mode coming from deeper, right? Than O mode, right? Usually, when we're talking about atmosphere, it's deeper is hotter, right? So therefore, the X mode emerging photon, X mode, X mode has dominant over the O mode. What Chris is referring to is that when you have a lot of messy processes happening in the magnetosphere, they particle bombarding the plasma, bombarding the atmosphere can, depending on where they stop, the particles stop, they may create a local temperature maximum. You may have a situation where here is hotter than here. Right, temperature inversion. So in that case, the whole thing is just wouldn't happen. Right? Completely would not be the right. So that's you tell me. This would not be. Will completely screw up this thing. It's certainly possible. Okay. You can preserve some aspect of this thing because you just almost right, and then the right. So a lot of issues here. Yeah. I don't pretend to know what's happening. Yeah.
You have the same question. Okay.
But more important.
Would you like a different answer?
Maybe Chris can comment on this other things. This is emission from from pair plasma. right? Your student Kostenko thing, right? That generating emission by itself, and then the question is how much that emission extend to 8 keV, right? That kind of things.
Well, it's
What's the uncertainty? What is the thing, right? That is
possible to have a Compton-izing layer at the surface, which upscatters in the manner similar to what people have long inferred for black hole corona, for example. Also, question about your cyclotron
yes.
transfer calculation.
Yes.
What geometry did you assume
Oh.
for the magnetic field?
Geometry. This is I'm just demonstrating a principle. This is, of course, where is it? This one, we just did the simplest thing, the dipole plus little twist, just add the twist. I didn't do even, there was this, everybody's using this, this model. This is this Thompson-Lutikov, Lutikov is here. I thought, yeah. Anyway, the elaborate model of twisted, I didn't use, we just put in some small twist for them to, and then parameterize this, the effect by the direction, right? And we didn't do exhaustive, we're still adding more effects. It's very too complicated for me. we did try to do it analytically, basically, okay? Right, and I mainly want to see whether this thing can be preserved. At least in some geometry, some conditions, this can be preserved. Okay, but again, the main thing is that this is not the whole story. Of course, the emissions, that's the thing we'll worry about.
Okay, thank you. I think I saw a request from Alex Chen. Can you make it to the microphone? No, for posterity, I will hand you the mic.
Yeah. So in this scattering model, my understanding is that spectrum between 3 and 8 keV is a power law, not like a black body, right? So can you produce the spectrum simultaneously with the?
We haven't tried.
We haven't tried. Okay.
Well, the paper, when they do that, we're talking about. If you go to high energy, clearly it's not black body. If you go to like 10 20 keV, that's a completely different thing. Okay, but at low energy, this thing is a little bit okay. You can do both. You can do black body 5 million Kelvin plus a little, and then or you can do 2 black body. They both fit. That's what they claimed. Okay. Okay, so that excess thing, people say, well, you can do upscattering using Compton upscattering, because the electron in the corona is mildly relativistic, can do upscatter a little bit.
But if it is from the corona, then it's kind of not the same as the surface where you have this multiple scattering, the optical from the optical depth effect that you were talking about.
This one, N0 corresponds to roughly optical depth of 1. I'm not sure I got the question. Roughly the resonant Compton scattering of order unity, of order 1. So if you're talking about very dense plasma, if the optical depth becomes much greater than 1, then this will be reduced. But the sign, yeah, I'm not sure. Yeah.
N0 is the minimal density decay current.
And not just this thing. Okay, so where is it? I just set this equal to this is V over C roughly 1. So basically the whole thing is 1. This whole thing. B phi or B polarized field divided by V over C, roughly 1. And then you, so okay, so could be the reality could be much larger, in order of magnitude, right? So that is twist of order 1, or V over C of order 1 correspond to tau roughly equal to 1. You can actually calculate that thing. I think that's true.
Okay.
I think that's true. Lutikov did this.
So, the scattering in the atmosphere is very angle dependent. And
scatter in the magnetosphere. This is the magnetosphere.
But if you're talking just about the atmosphere, the surface.
Yeah, the surface, yes.
At the very low energies.
Low energy, yeah.
That's very angle dependent. And so it depends on how you're looking with respect to the magnetic field.
Yes.
And how does all the mode switching and everything depend on this? And you didn't talk about that.
I didn't. Yeah, this is a very good question. So this is another thing I skipped, but it's actually very important. Very important things. I think what Alice is referring to. It's I have been talking about emission from a single patch, essentially, a single patch let's say, just zoom in a single patch of neutron star, and then if you put the polarimeter on there, they're highly polarized, and then the photon propagate to infinity. What Alice is referring to is, I think the question is, you are dealing with complicated neutron star where nothing, the surface maybe have very complicated B field, right? So it is true this patch has a linear polarization this way. This other patch also has the same, or the beam pattern is different, all the things, right? So naively, you would say, well, you have this complicated B field, different patch have different emission. When they propagate to infinity, they will cancel, naively. But that's actually not the case. This is actually not the case. Thanks to QED, this is actually recognized, I should have recognized by Neil Shaviv and Jeremy Heil, this is some years ago. What happens is that even forget the magnetosphere plasma, there's a QED effect, right? That means the two photon polarization mode has a distinct index refraction. So what happens is that the photon propagate from the surface patch towards the observer. The propagate, you're outside the magnetosphere, you're outside the plasma now in the vacuum. You're seeing the photon is gradually seeing a changing magnetic field, all right? It's actually polarization is not fixed. It's not parallel transporting. It's actually responding to the local magnetic field, okay? So this is what I'm indicating here. Here at the surface patch, this and this patch and this patch are very different, but the photon propagate towards the infinite, towards large distance, its polarization actually change. It actually move adiabatically responding to the local field. Okay, so that it's only at large distance it actually began to not care about the local field, began to so-called completely decouple from this thing. So now, of course, once you are far away from the neutron star, these two photons coming from different patches, they are equally far away from the neutron star. They see the same field, right? So they actually align. So the technical term is actually the polarization limiting radius. It's actually much larger than the radius of the neutron star. So at large distance, these photons from different patches undergoing different processes, when they come to a distance, they actually align. So they don't cancel. They don't cancel. So, okay, so polarization states photons from different patches star are aligned largely. No cancellation is actually indeed a QED effect for X-ray. Now for radio, of course, this is well known. Radio, the plasma effect, they decouple a large distance. It's similar kind of things, right? So this is actually, that is why you don't, actually with QED, this actually becomes simpler. The whole thing becomes simpler because you don't have to worry about cancellation because they all align because everything decouple at large distance. They all see the same right? So
it's nice to hear that someone has described QED as making something simpler.
Exactly. Yeah. This is one thing actually. The observed polarization direction depends only on the dipole component, regardless of surface structure.
Okay. Before we, I think we have a few more minutes left, so I will ask if anyone on Zoom has any questions, then do please raise your hand, and I will call on you. And while you think, I'd like to ask a question as well about the QED. So vacuum polarization is mediated by loops. It's a two-vertex process. And so I first think that, okay, if I only observe the outgoing photon, then I should look at other diagrams at the same order, which have a consistent out state, which would include one photon pair creation with soft emission and Compton scattering, and then any interferences between these,
yes.
So at the amplitude level. So can you just clarify, is that fed into your calculation as well?
Well, with the calculation I would describe, I did not have even actually you don't for this thing you actually don't have know anything about QED. All you need to do to trust. Look, so I often tell students don't let people mystify the thing, but complicated things. All this classical ENM, it's basically in this case it's just this formula, right? And the Heisenberg, Schwinger, all these people they did this already. It's a tensor, okay? So
true, but for a pure vacuum with only a field in the background, so. Right,
this is right, now what enter into this is what you described here. What you described is enter into these things, right? Once you have this thing, it's all done. The problem is the ENM problem. So I'm not sure I get your question, I guess.
Well, then I think perhaps we should discuss it over coffee. If there are no further questions, then let's thank the speaker again, please.
Thank you. Thank you.